In the previous video, we discussed wavelength and frequency, and we're going to find the properties of waves are highly dependent upon those two characteristics. So we can put the wave-like properties of electromagnetic radiation into something called the electromagnetic spectrum. And what that's going to do is that's going to kind of order all the different types of radiation in terms of energy. So I have this spectrum listed here, and over on the left is our high energy form of radiation, whereas over here on the right we have low energy. And it's given in this spectrum right here. And starting with the left, we have gamma rays, then X-rays, ultraviolet rays, visible radiation, infrared, microwaves, and radio waves. So as we go from left to right, we go from high energy down to low energy. Notice that the visible region of the spectrum, highlighted here, is just a tiny, tiny, tiny little sliver that our eyes can detect. And in terms of putting visible radiation into order of energy, remember that we have ultraviolet rays over here on the left and infrared radiation over here on the right that kind of straddle the visible spectrum. Next to the ultraviolet is violet radiation. Then over here next to the infrared is red wavelengths. So we can use the Roy G. Biv acronym to put these visible wavelengths in order of energy. Okay? Remember that ultraviolet rays from the sun are fairly potent because they're higher energy. Infrared waves don't have as high of energy. So over here on the left-hand side, you have the high energy radiation and the low energy radiation. So red, if we have a photon of red light, it has much lower energy than a photon of violet light, and I would expect you to be able to put all the visible wavelengths into the proper order based on energy. The scale that we're going to look at for most people's eyes, we have 400 nanometers is going to be the wavelength and the end of the violet region of the visible spectrum, and 700 nanometers for the red infrared region. This is going to kind of change. It's going to vary from eye to eye, but we're going to use 400 to 700 meters to list the visible spectrum. We also know that 1 nanometer, which is the unit we typically use for when we characterize wavelengths, is going to be equal to 1 times 10 to the minus 9 meters. So it's a very, very, very small length. Okay, so our high energy radiation in terms of the visible spectrum is over on the violet end, the low energy, the red end. If we have high energy, that means this is also going to be a high frequency, and the red wavelengths will have a low frequency. Remember that energy is inversely proportional to the wavelength, so 400 nanometers will have a short wavelength, and the 700 nanometer radiation will have a longer wavelength. So here we start to see the relationship between energy, wavelength, and frequency. And Albert Einstein was one of the first scientists to look into these relationships. And Einstein proposed that radiant light is composed of a stream of tiny packets called photons. And photons are the smallest increment of energy. And he developed, and scientists at the time developed a relationship for the energy of a single photon. So for a single photon, we can come up with a relationship that energy is equal to h times nu. And we can also say that nu is equal to c divided by lambda. So the relationship that we can come up with is E is equal to hc divided by lambda, where h is equal to Planck's constant, which is 6.626 times 10 to the minus 34 joules times seconds. And what this will allow us to do is this relationship will allow us to do various sample problems regarding and relating wavelength to energy and frequency.